Hi, and thank you for joining us. My name is Yochanan Lieberman. Here is what we're going to talk about today. We're going to begin by talking about container orchestration on AWS. Next, we will discuss the service discovery problem and suggest some practical solutions to it. We're going to talk about load balancing in the context of Docker applications. We're going to discuss the two types of autoscaling that exist when running Docker apps on Amazon. We will also talk about storage and suggest an architecture which allows easy sharing of data between your containers. And finally, we will discuss some strategies which could help you implement Docker-based continuous integration and delivery. Now, a general note, this is not a hands-on session, but rather a collection of best practices. And it is intended mainly for people who are already at least somewhat familiar with Docker and are either using Docker in production today or at least considering doing so. With that in mind, let's move on. This is the reference architecture we are going to use throughout the session. What you're seeing is an ECS cluster running Docker applications using a shared storage solution with an application load balancer on top and a Jenkins server for continuous integration and delivery. Now, we will go deeper in the following sections. Container orchestration on AWS. So what is container orchestration? Container orchestration is a general term for technologies which can help us manage large collections of containers easily. They allow us to deploy Docker containers on clusters and automate the container's lifecycle. But why do we need container orchestration? So one possible answer is you probably don't want your containers to look like this. So seriously though, starting and stopping containers manually using the command line might be practical when running a development environment on your laptop. However, when running a large-scale application in production, you probably need something else. We need to be able to achieve horizontal scalability across multiple servers. Sometimes we need to group together related containers. For example, we could have a container running a Python web app and another container running Nginx. And these two containers need to exist on the same host in order to work. And what about failures? If the main process inside a container crashes, that container exits. Who is going to make sure another container is taking its place? And what about updates? We have a new software version we wish to deploy. How do we update 100 running containers? And more importantly, how do we do so without affecting the service? So the answer to all of these questions is container orchestration. Now, there are many container orchestration solutions out there. Some of them are open source, like Docker Swarm, the official orchestration platform by Docker, or Kubernetes by Google. You might be familiar with some of them. Now, the guys at AWS have built their own orchestration solution called ECS, which is an acronym for EC2 Container Service. It is a proprietary solution which operates on top of EC2 and comes with a built-in private Docker registry called ECR. Now, ECS is free, which means you only pay for the AWS resources you use. That means EC2, ELB, etc. So there are many open source orchestration solutions. Why use ECS? So ECS is a proprietary solution, like we said. This means it cannot work outside of AWS. On the other hand, this also means that there are features which are unique to ECS since it integrates natively with existing AWS services. So for example, you can assign IAM roles to containers, which eliminates the need to use static API credentials if your application needs to access other AWS services. You can also use IAM to authenticate against your private Docker registry, thus eliminating the need to use static Docker credentials. You get a native integration with elastic load balancing and autoscaling, which we will cover in the following sections. And that's a new thing. You can also use Spot Fleet in conjunction with autoscaling to greatly reduce your infrastructure costs. This was announced about a week ago. And finally, you get full support from AWS, same as any other AWS service, and a promise for future improvements to the service. Now, ECS is composed of multiple components. We will walk through them briefly, as it's important to be familiar with these concepts in the following sections. So we have our ECS cluster. An ECS cluster is a collection of container instances. A cluster can and should be deployed in multiple availability zones. However, as of today, it cannot span multiple AWS regions. If you do need cross-region redundancy, you may deploy multiple clusters and add some sort of abstraction layer on top of them, like Route 53 or CloudFront. There are many solutions. A container instance is a regular EC2 instance which runs the Docker daemon. Now, container instances run a special Docker container that is called ECS agent, and it is responsible for communicating with the ECS service, or ECS platform, I should say. You may use one of the ECS optimized AMIs by Amazon. There are a couple of those. Or you may create your own custom AMIs and use them with ECS if you need to do so. As long as your instance runs the Docker daemon and has an ECS agent, you're good to go. You may deploy your container instances in an auto-scaling group. This is called cluster auto-scaling, and we'll cover it a little later. You may choose any EC2 instance type for your cluster. So if, for example, your application is very CPU intensive, you could select compute optimized instances for your cluster. You can even mix instance types within your cluster if for some reason you want to do that. ECS task. An ECS task is a set of Docker containers which are somehow related. Now, a task could be 1 container or 5 containers or 10. A task is the smallest unit that's handled by ECS. And for those of you who are familiar with Google Kubernetes, it is equivalent to a pod. Now, a task is deployed to a cluster, never to a specific instance. But we are guaranteed that containers within specific tasks will be deployed to the same instance. ECS takes care of that. A good example for a task might be, like we said, 2 containers, one running, for example, Python web app and another running Nginx. Okay, they are somehow related. Now, a task definition is a set of instructions for ECS telling it what to deploy. It's kind of a template for a task. So in the task definition, you specify which Docker images to use, which Docker volumes to mount. You can inject runtime environment variables to your containers, etc. In general, most of the stuff you can do using the Docker run command, if you're familiar with it, you can probably do with the task definition. Here you can also specify which IAM roles to assign to a specific task. Now, you may use the AWS console to configure your task definitions. You may also upload pre-written JSON files, or you can use the ECS API. An ECS service is another layer on top of tasks. Okay, it's an abstraction. It allows you to determine how many copies, so to speak, of a specific task you wish to have running at any given time, and automatically maintains the desired number of tasks. Even if a whole ECS instance fails, the service, the ECS service, will automatically launch new tasks on other available instances in the cluster to cope with the failure. A service may also increase or decrease the number, that number as needed, and this is called service autoscaling. We'll cover it in a bit. If your service needs to handle requests from clients, you may bind it to a load balancer. You don't have to, but you may. This can be useful for both private services and for internet-facing services. So again, here's the list of components just for review. We have our cluster, which is a group of instances, a container instance, which is an instance running Docker and host containers, a task, that is a group of related containers, task definition, that's a template for tasks, and a service, which is a group of identical tasks. Here's a diagram depicting a typical ECS architecture. We have a cluster of 2 container instances, and we've got a service which deploys tasks from a task definition. In addition, we have ECR, which hosts the relevant Docker images, and we have a load balancer, which makes the service accessible from the internet. So let's sum up this section. You can use ECS to manage your Docker applications on Amazon. You may also use one of the open source solutions. If you use ECS, it allows you to leverage the native integration with other AWS services. For production environments, make sure you build a cluster using instances in multiple availability zones to make it resilient to failures. And finally, choose the appropriate instance type for your workload, for your cluster, sorry, based on your application's needs. Now let's talk about service discovery. Question: how does a client know where to send a request when a service runs on multiple nodes? Now, service discovery is a mechanism which allows a client to automatically figure out where to send a request when communicating with a service. This might sound complicated, but as a matter of fact, you're probably already familiar with at least some service discovery solutions. Let's see what this is all about. As you may already know, cloud environments are very dynamic. They change all the time. IP addresses and ports could be allocated automatically by your cloud vendor. Autoscaling keeps changing the number of running nodes. Some of our instances might be under maintenance or upgrade and so on. With this in mind, how does a client know where to send a request when it wants to access a service? Now, this could be a mobile app user somewhere on the internet, or a web frontend that needs to talk to a REST API. It's the same concept. The moment you have multiple entities which provide your service, it could be instances or containers, you face the service discovery problem. Now, one solution is what's called a service registry. A service registry is just a database which stores up-to-date information regarding the service. It knows the IP addresses of the nodes, which ports they listen on, which nodes are under maintenance, etc. Now, there are several dedicated service registry solutions like Console by HashiCorp or etcd by CoreOS. However, a service registry is not a specific product, but rather a design pattern. It is just an entity which knows what's going on with your service. So, for example, a DNS server with health checks could also behave as a service registry by having multiple IP addresses for an A record. So in this example, we can see that the client asks the service registry where a certain service is. The registry replies with an IP address, and the client can now send the request directly to a node, which can provide the service. Now, this topology, as a side note, is called client-side service discovery. There is also server-side service discovery. Now, another maybe simpler solution would be to use a load balancer. If you use a load balancer, the client doesn't need to know the details about the various nodes. It simply sends the request to the load balancer, and the load balancer handles it. The load balancer, however, does need to know what's going on with the nodes, and it is responsible for forwarding the request to an appropriate healthy node. In this case, there needs to be some mechanism which lets the load balancer know when a new node becomes available or when a node goes down. Now, if you use elastic load balancing, this is handled automatically for you. This topology is called server-side service discovery. Now, to sum things up, cloud environments are very dynamic, so you need some sort of solution to keep track of what's going on. There are many solutions which provide service discovery. We recommend using load balancers when possible, as it greatly simplifies the architecture. However, in some cases, a load balancer alone cannot solve your problem, and you might need to use a service registry, sometimes combined with a load balancer. Let's talk about load balancing in the context of ECS. This is called service load balancing. Question: how can we provide a single point of access to a service which runs on multiple containers? So service load balancing is a mechanism which does exactly that. It can route traffic to multiple containers, not instances, containers. You can use service load balancing both for internal services and for internet-facing services. And service load balancing operates using elastic load balancing. And it makes autoscaling easier, which we'll see in a bit. So why should we use service load balancing instead of an open source solution like Nginx or AJProxy? A couple of reasons. Service load balancing integrates natively with ECS. It comes with built-in high availability and autoscaling, so you don't need to worry about failures or capacity problems. It also provides session stickiness, which may be critical for certain applications. It automatically checks that all of your nodes are healthy and stops routing traffic to unhealthy nodes. And it employs VPC security groups, which allow you to control who or what can access your service. As we said, service load balancing is powered by the ELB service, or elastic load balancing. As of today, there are two types of elastic load balancers. The first one is the classic ELB we all know and love. This one is a mature service which has been widely used for a long time now, and it can route traffic to multiple EC2 instances. The classic ELB supports layer 4 routing with some very limited layer 7 routing capabilities. And the classic ELB does not support dynamic ports. This is an important point, which imposes a big limitation when it comes to containerized applications, since many times their ports are dynamic. This is what an a classic ELB looks like. One URI, many instances, all of them are listening on the same port. Fortunately, a new type of ELB was launched recently by Amazon. This one is called Application Load Balancer, or ALB for short. This is big. The big news is that it has built-in support for containerized applications, since it can route traffic to ECS tasks or Docker containers instead of EC2 instances. It also provides the service discovery mechanisms for that. Now, unlike the classic ELB, the ALB supports path-based routing, which means you could use one ELB to route traffic for multiple ECS services. Also, if you do that, each service under that ALB can have its own health check. Now, surprisingly, the new ALB is actually cheaper than the classic ELB, even though it has more features. So you might be able to save costs by replacing your existing ELBs with ALBs, even if you don't implement path-based routing. The new ALB is production ready, and it has a long-term roadmap at AWS. So I suggest you just give it a try. This is what your architecture might look like when using an ALB. We have a single load balancer routing traffic to two ECS services. Each service has its own path. So one service could be, for example, /website, and the other one could be /API. This architecture is ideal for multiple microservices which belong to the same application. So to wrap this section up, there are two types of load balancers on AWS, the ELB and the ALB. We suggest that you use ALBs since they are cheaper and provide more flexibility. You may save costs by using a single ALB for multiple services by utilizing path-based routing. Now let's talk about autoscaling. Question: how can we automatically scale an ECS service based on load? Now the answer is autoscaling, which means automatically increasing or decreasing the size of your infrastructure based on load. You might already be familiar with autoscaling if you've used AWS for a while. However, autoscaling gets a little tricky when it comes to Docker containers, as there are two layers you need to take care of. We will see that in a moment. So when using autoscaling for ECS, there are actually two types of autoscaling. There is service autoscaling, which means changing the number of running containers, and there is cluster autoscaling, which means changing the number of instances in the cluster. Both types of autoscaling use CloudWatch metrics as their trigger. However, you should use different metrics for each. More on that in a bit. Before we talk about how to implement autoscaling, we must understand how resource allocation works in ECS. Now, this section is a little low level, so bear with me. On ECS, each running container gets a certain amount of the host CPU and memory resources. This capacity is reserved for each container. If there is unallocated capacity on the host, it is shared among all the containers on the host, and any container may use it. Now, you control the resource allocation for your containers in the ECS task definition. This creates a state in which every container is, in fact, a small compute unit. Therefore, increasing the number of running containers increases the service's capacity. The way CPU allocation works is as follows. Each host has 1,024 CPU units per CPU core. Each container gets some shares of the total CPU power based on what you've defined in the task definition. So for example, if a container gets 512 CPU units on an ECS instance with 1 core, it will get at least 50% of the host CPU capacity. Now, if no other containers are using the CPU, it may use even 100%. But when the CPU is shared between containers and there is load, it will still get at least 50%. Any container on the host may use the remaining capacity. The CPU units serve as a weight to determine how much of the spare capacity each container will get. Memory allocation, on the other hand, works a little differently. There are two types of limits here, a soft limit and a hard limit. A soft limit reserves a certain amount of memory for a container. However, the container may exceed this limit if there is enough available capacity on the host. Now, a hard limit also reserves some memory for the container. However, if the container tries to exceed this limit, it will be terminated, and another container will probably be spawned instead. You have to use one of the memory limits, but you may use both of them to achieve fine-grained control over the behavior of your resource allocation. So now we can go back to autoscaling. Service autoscaling means changing the number of containers running on your cluster to change the service's capacity. You configure it via ECS, not via EC2 autoscaling. Now, you should use CPU and memory usage metrics on CloudWatch for this type of autoscaling, not the reservation, the usage. You may also use application-specific metrics, but in general, the main question here should be, do we have enough compute power? If not, add more containers. Cluster autoscaling, on the other hand, means increasing or decreasing the size of our cluster. This is just regular EC2 autoscaling and can be configured from the EC2 console. Here we should use CPU and memory reservation, not utilization. Utilization is measured and handled by the service autoscaling we just saw. So the main question here for cluster autoscaling is, do we have room for more containers? If not, add more instances to the cluster. Now, combining the two types of autoscaling allows us to achieve a very fluid infrastructure, as we're going to see in the following example. So here we have a cluster with one instance and a couple of containers on top of it. Now, the average CPU utilization of our service is currently okay, and everything is stable. But at a certain point, the demand for our service might increase, which will trigger the CloudWatch alarm for our service autoscaling. Okay, the utilization is high. So we add another container. This seems to have helped a little. However, when adding another container, our cluster autoscaling alarm is triggered since we're nearly out of room now for more containers on our instance. So we add another instance. But as you can see, adding the second instance does not affect the CPU utilization of the service. We need to add more containers, okay, this is service autoscaling, to handle the load. That's a little better, maybe just one more. So, okay, CPU usage seems acceptable now, and we're back to normal. The cluster is stable. Let me summarize what we've talked about regarding autoscaling and provide our best practices here. Use both types of autoscaling. Using just one of them will either expose you to failures or induce high infrastructure costs. Now, for service autoscaling, monitor the utilization, and for cluster autoscaling, monitor the reservation. Now, an important point, service autoscaling is a lot faster since the launch time for a Docker container is typically less than a second, while launching an instance may take a couple of minutes. Therefore, when designing your autoscaling policy, always leave some spare capacity on every host. This will not only allow your cluster to scale in time, but it will also improve the performance of bursty workloads, which can use that spare capacity. Let's talk about storage. Now, storage is one of the more interesting, and if you ask me, problematic aspects of Docker. Let's discuss some storage-related problems and suggest possible solutions. Question: how to persist data used by a containerized application and share it among containers on multiple hosts? Now, as you may be aware, Docker containers are volatile. they are meant to be short-lived and their state isn't saved. Now, Docker uses a special set of file systems known as union file systems, or UFS, and data that the container writes to a union file system does not persist and also cannot be shared with other containers. So in order to store data persistently and share information between containers, we use a mechanism called Docker volumes. Now, Docker volumes bypass the union file system, thus allowing persistence as well as sharing of information between containers. You may use Docker volumes as a just virtual persistent directories within Docker only, or you may map host directories as volumes, allowing you to sort of export data outside the context of Docker. However, there is one big limitation here. Docker volumes are local to a host, which means the containers on one host cannot access volumes on another host. And there is no built-in synchronization or replication of data between volumes. So a nice solution to this problem is to use a shared file system. Now, there are many shared storage solutions. Two of them are EFS and ObjectiveFS. EFS is a shared storage solution by AWS. It's an acronym for Elastic File System. This is relatively new and is available only on 3 AWS regions as of today. Now, ObjectiveFS, on the other hand, is a third-party solution which employs shared storage on top of S3. It uses S3 encrypted S3 buckets for storage. Now, there are many differences between these services, and there are also other services I didn't mention. We're not going to go too deep into these here, but as a whole, both solutions provide similar capabilities. In both of them, you get a shared file system, which, unlike EBS, can be mounted multiple times concurrently. You don't have to worry about provisioning capacity, since these services are self-expanding, and you pay just for the capacity you use. And both solutions are highly available by design, which makes them suitable for production environments. Here's an example showing an EFS or ObjectiveFS volume that is mounted by 2 ECS instances as the /data host directory, which in turn gets mounted by multiple containers as /appdata, some different directory. So this way, the application can simply write data to /appdata, and all the containers will get this data in real time. To sum up our storage topic, use Docker volumes for any data your application generates, be it media files, log files, or anything else. Mount a shared file system on each host in your cluster. You may use a custom AMI to do this automatically. And map the relevant host directory as Docker volumes on your containers. Last but not least, continuous integration and delivery, or CI/CD. How to deploy applications to ECS and update them without service disruption. So there are a couple of ECS features which can help you perform CI/CD. ECS may use its built-in Docker registry or any other Docker registry. Now, you may specify exact code revisions by configuring Docker image names and tags in your task definitions. ECS has built-in support for rolling updates. It can gradually replace old containers by new containers without affecting your service. Updates to your service can be easily triggered using the ECS API, which allows you to automate the process. You may use Jenkins or any other CI/CD solution to talk to ECS and automate the deployment process. Here's an example. So here we can see a sample workflow you can easily achieve using ECS. Your latest code is checked out from the relevant Git repository into your CI/CD tool, Jenkins in this case. Jenkins then builds a new Docker image automatically, tags it, and pushes it to your Docker registry. In this case, we use ECR. Next, Jenkins updates the task definition and service on ECS. And from this point, ECS takes care of the rest and automatically performs a rolling update, thus replacing the running containers with new containers from the newer version without disrupting the service. Now let's talk about Docker tags, which are a crucial part when using Docker for CI/CD. Docker tags allow you to easily reference and classify Docker images. As part of building a Docker image, you must give it a tag. However, you may add additional tags later to that image. A tag is just a string, so you can use whatever you want there. In a moment, we will provide some suggestions on how to tag your images. Now, there is a special tag called latest, and it's special in the sense that it automatically gets used if no tag was specified when performing Docker operations. Now, some of you may be tempted to use the latest tag simply because it's the default without realizing the implications. So allow me to warn you there. If you use the latest tag in a CI/CD process, you might encounter weird problems. The main reason for that is simply because it's a static tag. It doesn't change. When you push a Docker image to a repository, and that repository already has an image labeled with that tag, with the same tag, the tag will move from the existing image to the new image, leaving the old image untagged. Now, this can lead to all sorts of problems, some of which are containers which look the same but actually have different code in them, or leaving multiple untagged images as garbage in your repository. These are images you will never be able to identify. There is, however, one good use for the latest tag, at least in my opinion, which is to suggest a default image on a public repository, for example, on Docker Hub, for your clients. So, for example, I could say, this image should be used by default if you don't know the product. So when in doubt, I suggest you avoid using the latest tag completely. So what should you use to tag your images? Basically, anything goes here, anything you want that's unique and meaningful to you. Here are some examples and suggestions. You may use your product's version. You may use the build number on Jenkins or your CI/CD platform, since it's auto-incrementing usually. You may also even use the SHA from the latest Git commit you used to build the image. Again, these are just examples. You may choose whatever tagging strategy you want. So let's wrap this section up. We suggest using Jenkins for CI/CD since it's free and it works great for both tiny and huge deployments. Trigger your Docker builds either manually or by using mechanisms like polling or webhooks. Build new Docker images automatically and push them to your registry. We suggest using ECR for private repositories since it's more secure than using a repository outside of AWS. Sorry, a registry outside of AWS. Have Jenkins update your task definitions and services on ECS to trigger rolling updates. And finally, decide on a tagging strategy and stick with it. And use the latest tag with caution and always as an additional tag, never on its own.